Hi. So last week I was involved in this big installation where we put a large 10-metre diameter LED display on the front of a major department store in the middle of central London. Now this consisted basically of 56 aluminium louvers, and there's a small sections, 200mm aluminium louvers with some white and some RGB LED tape. At the time we designed this we couldn't get the RGBW tape, so we used two separate ones. And these are installed in sets of about each of these is approximately 2 meters, and this is controlled by a little unit I designed that goes in this plate, which basically takes 48 volt power and RS485 data, and then drives 4 strips local to each one, because obviously with the 5 volt output we can't have long cables because you get too much voltage drop. I'll go into some more detail on this later on for the people that are only interested in the truck and battery side of things. Now whenever I get involved in a big installation like this, I always make up various test boxes and test leads. It's really important to be able to test anything, any part of the installation quickly and easily. You don't want to be dicking around with laptops, carting around mains leads or anything, especially for something like this where the power cable with these sort of huge great cable looms coming from an 8 kilowatt power supply rack. So I made up this is just a simple box to generate data for the LED. So the first use of this was when the LED strips were being cut to length and terminated. You just clip on and generate a simple test pattern on the LEDs just to show that that string was okay. Then when we were actually pre-building it, the LEDs were fixed down to the strips. The leads pass through and then these connectors put on. So we have a connector on here so we can just plug these in and just test it. It's just a very simple pattern just to show that data is getting through and all the LEDs are working. That's all it needs to do. And powered by this USB power bank, because again, you're climbing up ladders in a factory. You don't want to be messing around with mains leads, so you want to simply something you can just take with you, plug in and test. And the other thing this does, although these are normally 48 volt DC converters, they will actually run down to 18 volts, so you can actually power them from one of these sort of laptop style power banks that will put out 19 volts. So the other thing that we can do with this is we just plug the power in when all the strips are plugged in. This actually has some inbuilt test functionality, so we turn it on, it flashes the device ID, it shows the ID on the LED, and then it just lights up all the LEDs. So again, we can get a quick test. You can go run around the structure, plug this in, and basically test it easily without needing to go anywhere near a laptop or anything. Now obviously this thing was built in sections at the factory, because you can't really take a 10-metre high thing on a truck very easily. So it was built in 4 sections, so the idea was the sections would get loaded onto the truck. We had a very limited install window because we had to close off one lane of Oxford Street to get the crane and the cherry picker in. So the idea is the truck would park in a side road, then when we got the road closed we'd drive the truck round and then get it off the truck and install it. So again, to minimise any risk of any sort of problems, the idea was that while it was sat on the truck in the side road, I'd go up and just do another test. Now the problem there was that these are sort of wired in groups of 6 or 7, so each group has sort of this connector that comes out that then plugs into the cable loom, and because this sort of part assembled unit had 7 of these controls with this LED strip, its current draw, even when no LEDs are lit, was of the order of about 2.5 amps, purely just because of the quiescent current of everything. Although this power bank is technically rated for 3.5 amps, I didn't really trust it, and if we had to do any repairs, we'd have wanted to run it for a good few minutes, so I just didn't really trust this thing. So thought we'd need a slightly more chunky power supply for it. Now a few months ago my old battery drill packed up, so I got this Makita. This is a sort of current model DHP 480 18 volt, and I've been very impressed. I mean, the torque from this thing is just astonishing. So I figured the amount of power coming out of this battery is pretty decent. Pretty much any professional install I've been to, Makita's pretty much been the only game in town. I've not really used any other sort of modern tools, but all the pros it seems to be sort of Makita or nothing, as far as I can tell. So they're obviously very well respected. And of course, when I got this, I did take the battery apart. It's basically pairs of 18650s, 5 pairs in series. But the thing that sort of grabbed my attention is the fuse. It's got 2 50-amp fuses in parallel, so this is clearly capable of putting out quite serious amount of juice. So I thought, well, this is easily going to provide enough power to run these strips. 18 volts nominal, and when it's fully charged it's about 20 volts under light load, so that'll be more than enough to power 7 of these for probably maybe an hour or so, which is all I needed. So I made up this adapter. I used acrylic because it's what I had. It just happened to be the right thickness to fit these slots, so this just sort of clicks, latches onto the battery. It turns out acrylic wasn't really a very good choice because it's sort of obviously been dumped in the tool bag and stuff on top of it, so it's actually cracked. But yeah, this worked quite nicely to provide power, stable connections, a couple of copper strips to simulate the strips on the bottom of the drill. And of course I put a fuse in it because I only wanted to pull about 3 amps. I just stuck there's a 10 amp fuse in there just to avoid any fireworks if it gets shorted out, and a simple on off switch. Because one thing you've got to bear in mind is on a system like this, lithium batteries don't like being over discharged. Obviously a dedicated drill battery, it's the intelligence in the drill that decides when to sort of cut off. There's no switching in the battery because obviously you're switching very high currents, you've got potential for losses, so there's no point in putting a switching device in the battery apart from those fuses, which are obviously a last ditch. So that'll work. I got on the truck, tested it, all working fine, great. So waiting around the front for we got the road closed off, and then there seemed to be a lot of commotion going on. I heard someone saying, "Anyone got any jump leads? Truck's not started." So a general flurry. And of course I knew that trucks use 24-volt batteries because they're big engines, they need a lot of power to start them, and there wasn't any immediately accessible 24-volt vehicle to sort of drive around. The problem is that because we'd now closed the lane of the traffic off, the traffic was getting really slow, so it was very slow to move anything. The truck operator sent a guy out, but that was down in Kent, so that would take about an hour. So I sort of just started thinking, I thought, I wonder. So I knew that we'd have two separate 12-volt batteries. I had this battery, I had a way to connect it. The only thing I didn't have was any sort of decent heavy gauge wire, but fortunately my customer just bought a huge box of random bits of wire from their workshop just in case. So we found some, I think it's about 2.5 or 3 mil, it's probably maybe 12 AWG stuff. The reason these wires are so short is I just chopped off the fuse holder, stripped the wires, twisted this on, and we trundled up to where the truck was. Stuck a meter across the batteries, reading about 10. Each battery was reading about 10 volts, so it clearly wasn't a single cell. I think it's probably the fact that the truck was parked out the back for quite a long time. The guy probably had the lights on and radio and whatever, and that's maybe what killed the battery. Checking the battery voltage on the meter, we just stuck this across each battery for about a minute at a time for each battery. We did it a few times, one battery for about a minute, checked the voltage, and we got the battery voltage of each battery up to about 14 volts each. So we said, okay, give it a try. I mean, at this point, because this is it was costing a lot of money for the whole installation, so even if we destroyed the battery, that would have been a very minor cost compared to the cost of actually not finishing the install on time, because we had a very strict time that we had to get the road open by. So pretty much saved the day on a good old Makita battery. Afterwards the battery was pretty hot, so I didn't put this straight back in the car. I just left it somewhere just in case it was going to melt down. But I'm not really sure what the current was. But I mean, these wires were getting pretty warm. They weren't smoking or anything, but they were getting very noticeably warm after 20 seconds. So it must have been probably at least sort of over 50 amps that we were charging with, certainly at the beginning. So give it a recharge and it seems to be fine. So extremely impressed by these Makita batteries. They'll start a big truck and carry on working. Right, for those of you interested, I'll go through a few more technical details of this controller. Incidentally, notice that these leads are cable tied here. Now the reason for this is it's quite a good way of helping sort of protect these leads. If you've got a single wire going onto there, it's actually quite prone to flexing and sort of strands breaking or whatever. It doesn't take many flexes for that to get quite weakened, especially if you're sort of trying to stuff this into a cavity. But by simply cable tying all the strands together, each wire supports the other, so as you bend it, in this case we've got 4 in there, so every wire is basically supported by another 3 wires. So obviously you've still got some extreme cases like that, but for general movement, simply adding a cable tie actually gives you quite a lot of extra strength and protection on terminal blocks like that. Yeah, that's true for pretty much any sort of connector that hasn't got any really good sort of positive cord grid. Just simply tying all the leads together gives you quite a big improvement in its strain relief. So basically this is the control. It's this is both a cover plate and a heatsink. This is it without the plate. So we've got this is a 48 volt to 5 volt at 15 amp DC to DC converter. This is made by GE Critical Power, and for some reason they seem to be about half the cost. Yeah, this is a fairly industry standard package called an 1/8 brick. Brick seems to be a pretty standard format these days. So this is 75 watts, 5 volts at 15 amps. You can actually get these up to 150 watts, although they don't do 5 volts, which is pretty impressive for the size. And these are sort of planar magnetics. And they've got very good efficiency. I think they're about 92 or 93% efficient. As well as being quite cheap, the other nice thing about these GE ones is, although they're normally spec'd at 48 volts, they will actually run down to about 18 volts, which is really handy for testing, because obviously 48 volt supplies aren't nearly as common as sort of 24 volt or whatever, so they'll run on quite happily on 24, 48. You know, I've used these, for example, to run LED strips and servos from, you know, bunches of lipos and so on in various applications, so I quite like these. The other nice thing is they're isolated, which again can help avoid sort of ground loop. So, okay, you know, you might save a few pennies rolling your own, but just from the point of view of a package, you can just buy and plug in. These are actually pretty hard to beat. They've got good protection, you know, they've got overload protection, thermal protection. They're, yeah, pretty much indestructible. So on the rest of the board, we've got 48 volts and data in and out on this one connector. Obviously, we're using a big connector for the 48 volts, just so you physically can't plug it into one of the LED connectors. So you don't want it, yeah, 48 volts up the LED output would be bad. We've got a polyfuse for protection, and there's a common mode choke and some capacitors, because these things do actually kick out quite a lot of noise, so there's some noise filtering there. We've got a parallel diode for reverse polarity protection on there, and just an input capacitor. And for the data input, I really like these. This is an IL610. It's a passive input isolator. So yeah, it does a similar function to an opto isolator, but it doesn't need any power on the input side. So literally it's a 2-wire input. You don't need a reference ground, and it just takes, basically that input goes into just a coil and activates a magnetic receiver on the chip. And we've got a nice system where we've got both the data and the power is isolated. So for example, when we've got all these LED strips fixed down to a metal structure, we can actually tolerate a single short between either power and ground on the structure on one of these, and they won't affect any of the others, because they're all isolated and floating with respect to each other, so it avoids any issues of ground loops and gives you a certain amount of fault tolerance, which is quite handy. And this is one without the converter on it. The other protection we've got, one issue here is that we've got 4 LED strips, each one's pulling potentially up to 2 or 3 amps. But what we don't want to happen is for a short on a single strip to take the whole controller out, because we're running on the DC to DC converter. Any overload, even a brief load, it will trip out immediately, so that will lose the power to all the 4 strips and the control. So after quite a lot of looking, I was looking for sort of basically a protected electronic fuse, effectively. Okay, you know, we could use a polyfuse, but that wouldn't trip fast enough to stop the DC to DC converter tripping. So yeah, for example, if this was just running off a standard DC main supply, then we could use polyfuses to protect them. That would be fine. So basically what I wanted was something that would trip quickly and with a programmable output threshold. So I did quite a lot of looking. There's a lot of automotive devices. The problem is they don't generally run down to 5 volts. These are TPS 2557s from Texas Instruments. They're designed for protecting things like USB power outputs, and you can program the trip current with a single resistor up to 5 amps, and they'll trip pretty much instantaneously on a short circuit. The other nice thing is that the forward voltage drop, I think at 3 amps these drop something like 60 or 70 millivolts, so you know, they're not going to produce much heat when they're just running normally at fairly high currents. They've got like an on-off control, and they've also got a fault output that will tell you if it's tripped. So these actually work really nicely. So you can see we just have this running, we just short the supply out quite happily, nothing trips, it just carries on working beautifully. So that's exactly what we want. I was very pleased though. The only minor issue there in a DFN 8, but as long as you get the pad sizes right, DFNs aren't really that big a drama to deal with. And these LEDs, these are the APA 102 based ones. These are the ones that use a 2-wire SPI type interface. The main reason for using those in this installation was basically they were the only ones that we could get with white LEDs. This started off as a white only installation, and the customer decided they wanted pretty colours as well. But at the time they were the only ones that we could get white in, so that's the primary reason for using them. One issue though we discovered, although the actual controller chip inside these is normally, you know, has constant current outputs, when you're on at 5 volts it's actually running within its dropout range. So this means that when you're running a 5 volt LED strip like this, it is not driving at constant current, which means that if you change the supply voltage, the brightness drops. So in practice what this means is that if you've got any decent length of strip and you want to run a significant number of LEDs, you effectively have to, basically we had to feed power in at both ends just to avoid that. Otherwise you'll get a taper off down the strip because of the resistance of the PCB tracks, which was it was a bit annoying, but wasn't at the time, wasn't really any any other solution to it. It made the wiring a bit of a pain because we obviously had to take these down into the channel and run them back to the controller. Speaking of pulling wires, here's a quick tip if you need to do awkward wire pulling through, especially sort of through long structures. Now you can get various things like wire pulling tapes and so on, but they can actually be a pain to use quite often. So for example on here, our power and data feeds were coming in through cabled LANs on the edge, and we had to basically go in here and then across to the other side. So we had like sometimes like 4 or 5 metre pull to do. Simple answer: piece of string, nut on the end, and a big ass neodymium magnet. So you just stick the nut through and just drag it through so it comes out the other end. Another little tip: if you're pulling wires like this, obviously it's a pain to have to strip it just to get, a good purchase on it for when you put it on the string to pull it back. I found this is really handy. Just get a standard coil spring that's the right size. You can just twist that onto the end of the wire, and that'll actually hold the wire quite nicely to pull it back through. Just saves a little bit of time. I found over the years that just little, really simple things like this can, all add up to really saving a lot of time on installation. Because you think, okay, well, you figure out a method of doing one. It's then when you've got to do this, 20, 30, 40 times or whatever. Even if you're only saving, a few minutes at a time, or maybe just silly things like, you pull the wire and then you suddenly find you haven't got any tape, or the cutters are at the other end of the, 10 metres away. You've got to go down the ladder to get it. Just having little gadgets like this can actually add up to saving quite a lot of time and effort. When you're installing things, so it's always worth just spending a little bit of time thinking about all the tasks you need to do, and just making even just really simple little tools to do it. I mean, this is another one from another installation where this is actually a similar idea, where we were actually pulling through a curved carbon fibre structure that had quite a lot of rough insides. So this is just a dome nut with a little loop epoxied in the back of it. So this gives you a nice sort of fairly round surface to ride along the inner surface, and then just by having a hook in the back, it means we can just hook the wire in easily. You don't have to mess about sort of taping it or anything. So just little time savers like that can be really handy. But also, if you do this, make sure you make several of them up, because once you've found a nice method that works, there's nothing worse than losing this and then having to revert to other methods. So whenever you do stuff like this, just take a load of them, and away you go. Okay, back to this board. The rest of this is all pretty straightforward. This takes RS, well, it's technically RS422 because it's single-ended, but it's 485 because there's multiple items on the multiple devices on the bus, but it's one-way communication, so it's sort of one-way 485 technically. Oh, incidentally, these IL610s, so they're very nice because they've got that passive input. They do have quite a heavy load. It's not really practical to run more than about 7 or 8 of them on a bus, and if you've got a long cable, you need to be quite careful, because simply things like the resistance, if you're running over Cat5, you can have issues purely with the resistance of the Cat5, so you've got to be quite careful picking, based on the number of loads that you're planning to have, picking the right value of current limiting resistor on there. But if you get that all right, then they work really nicely, and they're good for I think they're rated up to 100 megabits. I've used them up to about 6 megabaud for standard serial data, and they just work really well. So basically this takes RS485 data at 4 megabaud. There's up to 7 of these on a single RS485 bus, and the whole system's got 16 RS485 buses, and we can get about 30 frames per second. So this goes in, there's a PIC32. Again, one thing I like about PIC32 is you can get them in like fairly nice big SO packages, so it doesn't have to be stupidly small, so you don't have to worry too much about solder bridging and so on. So this is all just SO, no fine pitch stuff. And even these DFNs, these sort of just flow quite happily. I think a batch of about 100 of these boards, I think I had 2 DFNs that I had to rework, so I was quite happy with that. So these APA 102s, it's basically an SPI interface. Now, although the PIC has got some pin remap capability, it is a bit limited. In particular, the SPI clocks can't be remapped. So we've got a couple of 74HC T08s here. Now these are doing 2 things. Firstly, they're doing a 3.3 to 5 volt conversion. Being the HCT, they've got a low input threshold, so if you power these from 5 volts, they'll quite happily work well within their spec on a 3 volt logic input. So those are providing sort of level shifting and buffering. But also they're also gating, so there's a line that selects which of we're driving 4 sets of strips, so we've got 2 SPI ports, so it sends all the data out to one strip, then it sends the data out to the other strip in turn, and these are just doing a simple sort of demultiplex function. And there's just simply some output resistors to reduce ringing on the output, also provide a bit of protection, so these can survive a short to sort of power ground quite happily. The only other interesting little detail on here, this is a Hall effect sensor. Now the reason for that is obviously there's 7 of these on a bus, and therefore each one needs its own device ID. Now I didn't really want to put dip switches on this. I'd not on an installation. My go-to method for doing IDs is dip switches because it's just easy. It makes replacement really easy. But because these are going to be mounted sort of under a plate, these boards are conformal coated just to help to reduce the effects of moisture. I didn't really want to put a dip switch on there, but also there might be a need to set the ID once it's been screwed down. It might simply be you've got the wrong ID and you screwed it down and you've forgotten about it. There's got a rubber gasket on the bottom to seal it, so it screws down, it forms a seal inside. So basically this whole sensor is used as basically an input switch for setting the ID. Now because you might be programming one of these on its own, just on the bench, or you might want to program it when it's under the plate in the system, there's actually 2 different ways of indicating the ID. Firstly, when you power it up, that flash just shows it's in the bootloader. Then when it turns on, it shows the ID as a number of LEDs on the LED strip. The colour also tells you the firmware version. One thing I forgot to do on this, which wasn't a huge annoyance, but would probably be nice if it had a way of identifying which strip is connected to which port by just having, say, a different number of LEDs lit or a different colour lit on each strip, just so that you can immediately tell that everything's plugged in the right way. But that wasn't a huge deal on this install, but it was the sort of thing I do tend to include. I just forgot on this one. So as well as the power on indication, if you stick a magnet on it, you then get a flash, so you can see the number of flashes. That's 2, 3, 4. So as well as the number of flashes, it also shows it on the strip. So if you're programming it while it's bolted down, you can see the ID on the strip. If you're doing it on the bench with no strips connected, you just look at the number of flashes. So you just turn it up, hold it briefly, just shows 4 flashes, gives you the ID. If you keep holding it after it's shown the ID, so that's 4, then goes to 5, etc., and it goes up to 7, then resets down to 1. So that's quite a neat way of setting the ID in a sort of situation where you've got limited access. Oh, and of course what I was saying about making sure that you take multiple copies of any special tools, make sure if you're using something like this, make sure you've got plenty of magnets. This one actually put in a little cable gland with a keychain, so I can attach it to the test box. In fact, on one of these test leads I actually put some magnets and some heat shrink on the cable, because there's nothing worse than having a system like that and then having to scrub around a build venue or something just to find a magnet. They can actually be surprisingly hard to find if you're not careful, so just make sure you take plenty of tools with you for doing that sort of thing, especially on that, because that's under the plate. That needs a fairly powerful magnet just to work through that distance. One thing to watch on these hall sensors, I think this is maybe a Seiko one, there are some which are latching, where basically what you want is something which you just gives you a momentary output. You can see the LED indication, just gives you an on-off indication, but there are some which one pole they'll latch on and then you use the other one to latch them off, which aren't that useful. There's another installation I've done where I needed, basically it was a sound player enclosed in a die-cast aluminium sealed case, and we wanted the ability to turn the volume up and down, because obviously we had to screw the front on to close the enclosure, to close the speaker to get the right sound. So we wanted a way of adjusting the volume without opening the box, so we used a bipolar sensor, and this one was actually sensitive to the polarity of the magnetic field. So what you could do is it gives you 2 outputs. It gives you like a polarity 1 output and a polarity 2 output. So if you hold the magnet one way, one output will go. You hold it the other way around, the other one will go. So we used this as a volume up, volume down mechanism, which that worked really nicely. So you've got the is the magnet there or not? Putting the magnet close would turn the thing on, activate it, start it playing the sound, and then by putting the magnet either way you could actually turn the volume up and down to adjust the volume inside this sealed box. Obviously in a sealed enclosure, when it's something you only want to do at install time, you don't want to have a break in that enclosure for an external switch or a key switch or anything like this. So the magnet was quite a nice solution. Obviously if you wanted more controls, you could probably put 2 sensors in different places. So as long as you knew where the sensors were, you could get some indication. But magnets, hall sensors, quite useful things. And this is another test unit I made. This was for when I was testing the assemblies on the back of a truck. It's a PCB from another project. It just happened to have a PIC 32 and a 485 transmitter on it, so it was just convenient. Just to bang some simple code into it. I just wrapped it in this bit of huge heat shrink. It's a quick way of protecting it. And basically what this does, this generates data going into the all these controllers. So it generates a sort of simple test pattern that will light up the strips and just show some test patterns. But it also shows It gives two indications. The blue is the ID that this is currently sending to light up, so it lights one at a time just to avoid taking too much power, because at full power this lot will take 8 or 9 amps at 48 volts, so at 18 volts the current will be a bit ridiculous. So it lights one strip at a time. So this lights up on every strip to say what the ID is of that controller, and then this is the ID that's currently been sent. So that's number 5. So when the address gets to 5, it lights the whole strip up. So again, that allows us to very quickly, you know, when all 7 they're just pressing their button, you see each strip light up on each louver in turn, and then you just use the scrolling pattern just to confirm that you're getting data and it's no glitches or anything, and you're getting a sort of sensible pattern from it. So again, that was really saved a lot of time, because again, you know, climbing on the back of a truck in the rain, you really do not want to be messing about with a laptop. You just want to plug it in, press the button and go.